books on 295 South. No lie. On their That's exactly right. Crazy. Alrighty. So before we get going, what questions do you have? Because this would be a really good time for that.
What is the equation for atmospheric O2?
Oh, it's just oxygen is O2.
Just O2?
Yeah.
Why is it called atmospheric?
Well, it's because you're getting it from the atmosphere instead of us releasing it from a bottle.
Oh, okay.
Yeah, 20% of the air is oxygen. All right. Anything else? Questions, concerns, or prayer requests? If you have been working on your total and net ionic equations, if you would give me what you have when you start lab while you guys are doing lab, I'll look through whatever I can and give you some feedback on it. Is there a question underlying there? Okay, so let's look at another one just because I suspected this was the unasked question. All right, I'm going to do one that's a redox because that's the other issue that people have. You're welcome. You'll thank me for this later. Zinc plus HCl. What kind of redox reaction is this? Yeah, maybe you can. Oh, smarty pants. Yeah, just a second. Thanks for asking. All right. So zinc plus HCl, what kind of reaction is that? It's not an ionic equation yet. You have an element plus a compound. What kind of single replacement? Single guy walks into a bar and he's trying to steal somebody's date. Who's he going to try to replace? The hydrogen, because we know that zinc would like to be the cation portion of this. Now, zinc is higher than hydrogen on the activity series, which is how we know. Everybody okay on where we would find the activity series? Okay, I had a feeling. If you look at the appendix page, when you look at your solubility rules, at the very bottom of your solubility rules, wait for it. There we go. Activity series. We see that zinc is here and hydrogen's here. So since zinc is above hydrogen or greater than hydrogen in terms of activity, then this replacement can actually take place. If hydrogen had tried to replace zinc, nothing would have happened. But because zinc is greater than hydrogen on the activity series, then he can replace it. Now what that means is that hydrogen is going home alone as an element. And zinc is going to steal hydrogen's date. All right. Now, since this was binary, we know that this is monatomic and this is monatomic. What charge does zinc get when he's in a compound? 2 positive. What charge does chlorine get when he's in a compound? 1 minus. So is this neutral as written? No. So we crisscross to make sure that everything ends up being neutral. Now, elemental hydrogen doesn't look like this. What's wrong with it? He comes in 2s. Good. There's 7 diatomics, just as a reminder. They make a 7 on the periodic table and then hydrogen there. Nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. These all come in 2s in their elemental form. Now, to get the states, zinc is a metal, so metals are usually solid. Who's the only metal that isn't a solid? Mercury. Good. Hydrochloric acid, if it's named that way, we know he's aqueous. Because you wouldn't call him hydro anything if he were not aqueous. Hydrogen is a gas. How would I know what physical state zinc chloride is going to be in? On. When it comes to states, how do you know? Solubility rules, sure. So that very same page, we would look up zinc and we'd match him to chlorine. And what do you know? He is soluble If he is soluble, that means that he is aqueous. Yes.
It was a little hard to like follow what they were saying in the book. So if it's not on this chart, then it's probably insoluble.
Not necessarily. I gave you, for example, some of the ones that are the most common. And I mentioned, or if maybe I didn't, but I did, that if you're looking for mercury 1 tracks whatever silver does. These are just some of the common metal cations. So we're not going to guarantee about any others, just these are the ones that are really common you're likely to see.
So we're not going to have any.
That is correct. And if it is something that's missing from the chart, let me know and I'll tell you, because again, these are just the ones that are most common. So because zinc chloride is soluble, then it is an aqueous solution. And yeah,
It's insoluble, but it's
solid. So the solubility rules. Soluble means aqueous always, and insoluble means it's likely to be a solid. And liquids are pure, whereas aqueous means it's mixed with water. So water is the only pure liquid you deal with for the most part, unless you're talking about elemental bromine and elemental mercury. Good question. All right, so just to top this off, we need to balance it. We got 2 chlorines on the right, so I'm going to need 2 HCl's, which then works for our hydrogens, and our zincs are working out. So this is as written. Clean it up a little bit. This is what we call a balanced molecular equation. In a molecular equation, everything is neutral, which means that we've crisscrossed as much as we need to. Everything's neutral, it's balanced, and it shows states. Again, the states, for the most part, unless it's an element, come from the solubility rules. We said that there were a few things that were gases you needed to look out for. 3 of them in a cloud and then 2 others. But this is our molecular equation. Are we okay? Now, the next portion isn't that bad, but you really need to pound in the rules. The rules say if I want to go from a molecular to a total ionic equation, which is the next version, I need to dissociate or ionize, in the case of strong acids, any strong electrolytes. Which means that we probably need to be really confident about what strong electrolytes are. There's only 2 types of strong electrolytes. First off, they must be aqueous. If they are aqueous and they are metal compounds, meaning that they are ionic. If they are aqueous and strong acids, then they will be strong electrolytes. So not everything is a strong electrolyte. We need to look for the things that are. Now, if I look at my states, the solid and gas are out of the running because the first statement is that they have to be aqueous. This is aqueous. Is this on my list of strong acids? Yes, it is. There's only 7 strong acids, and he's one of them, which means that this one is a strong electrolyte. This is aqueous. Is he on my list of acids? No. Is he ionic? Yes, it's an aqueous metal compound, which means that this one also is a strong electrolyte. So when I go to a total ionic equation, I only get to change those 2. Everything else is still there. It's just written differently. So zinc carries down because he's unchanged. This is binary, right? Would you agree that that's a binary compound? That means that I have monatomic ions. How many hydrogens do I have? How many chlorides do I have? Because again, I still have to count for them. It still has to be balanced. Yes.
Do we have to put the plus on the H? And the
Yes.
Y on the- okay.
Because it's an ion now, whereas it wasn't a neutral compound. Once it breaks apart, they're no longer connected, so they haven't canceled each other out. Notice that we don't get to change anything other than breaking them apart into the separated ions. So I don't get to change their states because that was what allowed them to break apart. Now this is a gas, so I can't do anything to him, just copy him down. Now this one's going to break apart. Again, he's binary. That means he has monatomic ions. Zinc being a 2 positive, chloride being a 1 minus. How many zinc ions do I get? And how many chlorides do I get? 2. Because the 1 times 2 tells me I have 2 total of the chlorides. Remember that monatomic ions don't have subscripts if they're dissociated. They lose a subscript when you dissociate them. Where does it go? It has to become then a multiplier. What state should these be?
Solid.
What state would they? So you don't get to change the states. That was established in the molecular equation, and it stays consistent throughout. That's the number 2 most common rookie error, is that everybody wants to change states because you've broken them apart. The only reason it could be broken was that it was aqueous. So pretty much in later chemistries, very commonly, if they show you an ion, they won't bother mentioning that it's aqueous because they know that you know that's the only way it could be aqueous. And hopefully by then you will know that. Which brings us to our net ionic equation. This time we need to get rid of anything that's identical on both sides of the equation. Is there anything that's exactly the same? Things not exactly the same. Changed state, changed charge. The chlorides, exactly the same state, charge, and formula. So if anything's changed, then it is not a spectator. So I'm going to get rid of that because nothing happened to him. I'm only going to include the things that actually changed. So zinc, solid, reacted with 2 hydrogen ions, aqueous, to form hydrogen gas and zinc ion, aqueous. I'm sorry? That's where it is. That's why I'm here. All right, the next most common question, and some of you haven't gotten to this one yet, so you don't know that you have this question yet, is we're going to compare what happened. If I look at what zinc did when he started out to where he ended up, he went from an element, which implies that he had no charge, to an ion with a 2 positive charge. Notice he went up in charge because he went down in electrons. Remember, you can only get a charge by gaining or losing electrons. If he had gained electrons, what would happen to his charge? It'd become more negative. Would you agree to that? So oxidation is the loss of electrons. He went down in electrons because he lost them. How many electrons? 2, because that's the difference in the charge. That's why we talked about that back in chapter 4. We said if we have the same protons, but we have changed the electrons, then we have a charge now. So if I look at what happened to hydrogen, it went to an elemental form with, again, a zero charge, because elements don't have a charge. Molecules don't have a charge. The only things that have charges are dissociated ions. Now I can see that my charge went down, which meant that I had to have gained some electrons. And the reduction is the gain. But now we can see why it's called reduction, because we reduced the charge.
Okay, so I gain
Well, let's look at that. Individually, the hydrogen gained 1, but I had 2 hydrogens. So collectively, there's 2 electrons that were gained. Moral of the story is you can't gain electrons unless there are enough, the same number of electrons being lost by something else. That if you're going to lose 2 electrons, there better be somebody else around ready to take 2 electrons. And so each hydrogen went down by 1, but I had 2 hydrogens, so a total of 2 electrons were needed. So reduction is the gain of electrons, oxidation is the loss of electrons, and the reason it's called reduction is because the charge was reduced. The charge became more negative. Which brings up the next question that bothers most students, and that's about agency. Only the things that are on the left side of the equation can be agents. So when you're asked about an oxidizing agent or a reducing agent, you can only look at the left side. Now, what happened to zinc? Zinc was oxidized, right? Remember, your agent, travel agent, doesn't take the trip? If he was oxidized, this is our reducing agent. Travel agent doesn't take the trip. The reducing agent isn't reduced. He's oxidized so that something else can be reduced. Which makes then hydrogen what? The oxidizing agent.
Can you explain that? It doesn't make sense.
I apologize on behalf of all chemists worldwide. We don't like this any more than you do. But an agent allows something else to be acted on. Right? An entertainment agent is not the entertainer. So when we say that this is the agent of something, it means he's allowing something else to be reduced. The only way that something else could be reduced is if there's somebody willing to be oxidized. So because he was oxidized, by doing that, he was the agent of some other substance's reduction. The agent allows something else to take part. So this substance was reduced, which means he's the agent of somebody else being oxidized. I know, it sounds backwards, but if you think about the travel agency thing, it sort of helps you along the way. Your travel agent doesn't ever take the trip. Your oxidizing agent is never oxidized. Yes, and I hate that they did that too. I hate that for all of you. We ready? So I wanted to bring this back around to you because I suspected that by about now some of you might have looked at some of these and realized you had a couple questions. Or maybe you didn't, then boy, is today going to be harder. All right. So last time we started talking about general relationships. Now, I did an exercise with my morning class, and I'm not going to lie. They all tried to weasel out instead of using this little chart. And then every group that did exactly what I told you not to do had problems with it. This should be a 5-minute out of the park. This is an easy problem. Don't make it harder than it has to be. Take the time to learn the basic relationships. Sketch this little thing until it is absolutely natural for you. Because if you do, you can work the first half of all the problems in chapter 8, very simply. So either we are counting by individual particles, or we're counting by a package. We said this was a 6 times 10 to the 23rd pack. Which means that if I'm comparing size, this size of the chart is small stuff, and this side of the chart is large stuff. We said that there is one number that will link any small to large, and that number is Avogadro's number. Whether we're talking about counting quantities or whether we're talking about these particular units of mass. And that number is Avogadro's number. We said last time, 6.022 e to the 23rd. Are we okay so far? Now, remember that it's always used that Avogadro's number of the small things is one of the large things. Always, always, always. And again, this is the small side. Now, last time we introduced the idea of formula mass. We said formula mass was what happened when you look at the formula and you add up the mass of everything there. For example, for barium phosphate, we have 3 bariums that each weigh about 137.3. We've got 2 phosphorus at roughly 30.97. And we've got 8 oxygens at roughly 15.9994. So collectively, it adds up to about 610. Now, here's the thing that's magical and mysterious. And that is that that same number, this formula mass, can be used 2 different places. It's used here and here. It's exactly the same number. The only difference is which units we use. If I use it here, it's relating these 2 units. If I use it on this side of the chart, it's relating these 2 units. So I call it typically the formula mass if I'm talking about an individual molecule. And so it's relating U's and formula units in this case. Why am I calling it formula units? Because this is an ionic compound. And that's what that particle is called. Just a reminder that particles are pretty much 3 different names. Particles could be atoms. They could be nonmetals and some other stuff, in which case we would call them molecules. Or they could have a metal in them, and then we would call them formula units. So these are just all different types of things that could be collectively or generically, non-specifically called particles. Are we okay? So it turns out that this same number can be used also here. Same number of top and bottom, same number left and right. This time, the units that it's linking are grams and moles. So let's look at why that is. If I know that for this substance, there's 610.332 U's for every 1 formula unit of that substance. This is what my formula mass is telling me. And I want to get the same information this time in these units so that it will link these 2. That means that I'm going to have to take my U's and convert them into grams, because those are talking about mass. And what number relates U's and G's? Avogadro's number. Which one's smaller, U's or G's? So Avogadro's number always goes with the little guy, and 1 is a placeholder for the other substance. And now our U's are gone. So we've converted the mass portion of it. Now we want to convert the formula units into moles. So if I want to go from formula units to moles, why did I put formula units on top? So they'd cancel when I multiplied out. Again, this is a small to large conversion. Which one's small, formula units or moles? formula units. So we can see that the formula units are going to cancel, but we can see also that N is going to cancel, which means that it's exactly the same number, 610.332, but now our units are grams per mole. It's not actually magical. It's because we chose to define the gram the way that we did. We got to create all units of measurement, and we defined the gram in such a way that this would always be true. Just makes our lives a little easier. So let's look at using this information. We're told that the molar mass of CO2 is 44.0098. How do you think I came up with that number? Periodic table. How many carbons? 1 carbon at 12.0107. How many oxygens? 2 oxygens at 15.9994. Combine those, I came out with 44.0098. So it's not completely magical, it's just calculating the formula mass, because again, the formula mass and molar mass are the same number. The difference is what units we have. So what we know this time is that we have 1.55 moles of CO2. And the question wants to know, what is its mass? Now, this is where this little chart becomes helpful. Let me get rid of all this stuff here. We are here. Which unit of mass is closest to it? Grams. So it makes sense to describe this one in terms of grams, because they're both large quantities. Along the same lines, I don't weigh out my car in ounces because it's not meaningful. We use the unit that's most reasonable for the quantity. Now, in order to do that, I need to know the molar mass. Well, I got that part. Just a reminder that because he's a mass, he will always go with the unit of mass. That number will always go with either G's or U's, because these are both the units of mass. And the other one's a placeholder. In the follow-up question, we have 10 grams of CO2, and the question wants to know how many moles. Well, I am here. In one step, I can go from grams to moles. What information relates grams to moles? The molar mass. Would you agree to that? So I look back to his formula mass, because formula mass and molar mass are the same number. And again, this is a mass that goes with the unit of mass. And then 1 is your placeholder. So essentially, I'm setting it up just so that my units cancel, and then I'm filling in the relationship. Well, let's say that I have, let me zoom out a touch here, 3.5 times 10 to the 8th U's. And the question this time wants to know how many molecules. So I want to go from U's to molecules. And that is the correct abbreviation for molecules. Just FYI, molec versus MOL. Yeah, that's the abbreviation for mole. I don't know why they even bothered. Molecule. So they're different symbols. All right, so I'm going to go from U's to molecules, and I know that a molecule is a type of particle. I can see that this should be a one-step conversion using what piece of information? Not from these two. Avogadro's number only does left to right. This is going to be where I use my formula mass. Mass and counting units are not small to large. They're just different quantities. So I have to use my molar mass as my relationship. So since I'm still talking about CO2, 44.0098, goes with the mass unit for every one molecule. Are we okay so far? All right, so we have in the next one 2.33 e to the 16 molecules of hydrogen. And the question wants to know how many U's that is. I am here. U's is one step away, so I can go from molex to U's. And what information relates those two things? Yeah, molar mass, formula mass, whatever you want to call it. Because it's H2, how do I figure out his formula mass? I got 2 hydrogens at 1.00794, 2.0158, I think, used for every one molecule. Are we okay so far? Again, find where you are on the square, and then work your way to where you need to go.
Formula mass, molar mass, same.
That's exactly right. Same number, different units. So there's only two numbers that will take you all the way around. Either the formula mass or Avogadro's number will do it. You just need to know which one to use. Avogadro's number only works from small to large. The masses relate particles or counting units to masses. So we just call it mm over here and formula mass over here. And they have different units because they're linking different things. So we're going to look at option B here. We have 6.33 times 10 to the 22nd molex of a misnamed substance. That should be monoxide. Shameful. Question this time says, I want to go from molex to grams. Oops. Molex being molecules, right? We are here. How many steps away is grams? 2. We actually have 2 different ways we could get there. We could go to moles and then to grams in 2 steps. I can go from molecules to moles, right? That would take us here. And then from moles, I can go to grams. Or I could go from molecules to U's, and from U's to G's. Either one of them would work. So if I were going the first way, the one to the right around that cycle, is everybody okay with why I know that that's a 2-step process? That's why we draw the square. And every group this morning that tried without it then got lost because they didn't know where they were headed. This is the map that tells you how everything connects up. So if I want to go from molex to grams, or molex to moles rather, what relationship takes me from here to here? Avogadro's number. Now Avogadro's number is a small to large correlation. Which one's small? Molecules. What information links me between moles and grams? The molar mass. Because it's a mass, which unit gets it? The grams part. We'll come back to the numbers in just a second here. If I were going the other direction, between molex and U's, what information relates the two? Formula mass, right? Isn't that what connects those? Because it's a mass, which unit does it go with? The U's. And if I'm going from U's to G's, what information relates those? Avogadro's number, which one's smaller, U's or G's? U. So Avogadro's number goes with the little one. We just ended up doing exactly the same calculation, but in reverse order. We're going to get exactly the same number. It doesn't matter which way you choose to go. So let's take a moment and figure out our molecular mass. This thing just hates my pen. So 6.33 e to the, oh, sorry, I don't want to do that one. I wanted 2 nitrogens at 14.0067 and 1 oxygen at 15.9994. Gives me a formula mass of 44.0128. A lot of times, if they give you this information, they'll just say something like mm equals 44.0128. They won't give you units because they know that you're going to use them however you need to use it. Sometimes they'll just give you this right next to something. If they told you 6.33 e to the 22 molecules of N2O, and then right next to it they just say 44.0128. This number is always the molar mass. They're just saving you some time by calculating it for you. Yeah. Exactly right. This is why we, which periodic table are you looking at? Okay. This one here? The IUPAC periodic table? When you say two different numbers, which one do you mean? Okay, so that's it. Okay, that's this one like a 2 here. Ah, okay. What that typically means is that there's 2 major sources of data and that they haven't confirmed which is better. Most tables will average them, but these are the most common measured values. Remember that molar masses are measured experimentally. And so what that means is that IUPAC hasn't decided which is the more accurate measurement. Most periodic tables will average them. When you're working on homework, as I mentioned last week, always use the periodic table in your book. And if you're taking a test with me, everybody will have the same periodic table, so we wouldn't have that issue. That's a very good question. I just wanted to make sure I was hearing what you were telling me. Okay. So when I need that number, 44.0128, it's going to go with grams or with U's. Now, I don't care that you write out the 6.022 e to the 23rd everywhere, but if you're going to use the symbol, which is totally fine, I do to save myself time, somewhere on the page you should define it, 6.022 e to the 23rd, and then everybody knows what that means. So you'll notice that, and I mentioned it on the next page, the section in your textbook about volumes in section 8, we're not going to discuss yet. We'll cover that in chapter 10. So not yet. Because they talk about gas behaviors and we haven't talked about gases at all. So we're going to hold off on that. Now, it's one thing to watch me do it. It's a whole nother to do it on your own. So listen up for your numbers. this is how this chart works. This is your given quantity, which means that if you're on the chart, I'll give you a little kickstart here, GU, moles, and particles. You are here. Your task is to work yourself around the circle to finish the rest of the information. The reason I have a chart or a place for this is you're going to need that number. So I want to make sure that you can calculate that as well. If you are working in this group, then you are starting here. And you'll work your way around the number to fill in the other pieces of information. So that's how that works. So listen up for a number here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1 and 2. So groups 1, 2, 3, 4, 5, 6 is normal. Sorry? We will, yes. You need scratch paper? Oh, we'll do the other ones together. This is what you're doing as your Inga. Okay.
How are you doing? She mentioned all this, but it's not.
Get out on this.
Oh, you guys are working on this? So whatever scratch
On
paper
this
you
sheet
have.
or a scratch
You
paper.
can do it however you want to do this, because just like in normal Inga, you're gonna have to come up with an answer.
Yeah.
Alright, so first time,
Do it on the camera.
Everybody needs scratch paper, you can
and we're trying to make our way.
come on down.
Let's do. Each two. Two times.
I know, it's glorious.
One time.
Are they like the best or something?
I don't know. It's the best I've ever owned. I like my office. Yeah.
Right?
When
Your
you find one
office.
that works.
Figure them all out.
So this is the one that's also
You sound awful. You okay? You sound awful.
Oh, I'm fine.
Yeah, today's, it's okay. Yesterday was awesome. I have no idea what was the deal. I've got some sort of autoimmune thing. I have no idea what it is. They're still testing me. But it's, no, it's,
Or an alligator.
no,
No, this is one that, they've tested me for rheumatoid. I came back negative. They're testing me for scleroderma, for lupus, for, I have a massive immune response to something. They don't know what it is. And my joints hurt all the time. Some days are way worse than others. Well, I thought it was, well, she said, my rheumatologist says she's not sure it's not rheumatoid. Some people don't show up, so they did, all day yesterday was imaging. They did like 60 different x-rays of every joint in my body is. It is what it is. Everybody's got something.
I mean, we don't want to have,
No,
we can prevent, we can do something to do it.
Yeah, I would totally like to do without, but
Have you tried those super from those people? You know what I'm talking about, super, you're super.
I have to be very careful about things.
Well, they're naturals, there's supposedly only 6 ingredients in each thing.
Even naturally,
Yeah.
I'm allergic to things, whatever reason.
Do you know what you're allergic to specifically now?
There's no testing some of those. We're not even sure. And I know that I have no kidney. I'm missing one kidney, my gallbladder. Anyway,
So these things can have,
Yeah.
same certain organs.
my body does not like me.
It's attacking you, you're attacking yourself. I'm just a very firm that foods and
I am all about cooking fresh.
That's
And
good.
that
Not
I
processed.
grow vegetables. Yeah,
Yeah.
I'm all
Which
about
is good.
that. I don't eat fried anything.
That's good.
It's like 1 0 times 10 to the
Avocado's number. Somebody said avocado is standard with a formula, and that's his freaking number. That's what it is. That is it. And it's this. These are crazy. Somebody knew avocado was a one, and he gets it right.
So can you do 2 white, 2 0 use?
What's the question?
I was just confirming that whenever you put N and you put G, you put N, that's the point.
Yeah.
Yeah, it's like a place.
Yeah, it's instead of having to write that number every time.
Yeah. Yeah, so you have top, and then use your using that as a yeah, but I use it, so now we don't. So that's not my system. What if it said that? Would you freak out? So this number, I love to memorize. Because this one has 2 decimals, so.
So we're going from grams. So you think we put it in the numerator? Why is it?
We're just finding.
Oh.
Old mass number of. Then we can start.
Like 6, 5,
So if you do this number.
This next part is oh wait, that's
Like leave off this part.
I think so.
Or should we?
now, right?
And we know avocado is not because she can't feel about the avocado. What was the joke? I can't say no, there's a joke that she has with avocado.
It's in the
It
this
is
section.
Halloween.
That's right,
That's
probably,
why I know what it is. I want you to know that.
That's
So
it.
it's not going anywhere.
it's like guacamole.
Yeah, guacamole. Oh, that's good. It says what happens when you.
You get when you cut an avocado into 6 times 10 to the 23rd pieces.
Oh, jeez. But and it's avocado, which is avocado. I like it. That is good.
It's chemistry cat. You see the memes.
You know, I read that joke before we did the lecture, and then you said it's avocado, and I was like, now the joke's funny.
Exactly.
Do we have a left and right? This way?
You suffered elementary school.
This way?
Just
and
for
that way? Or mask?
this, opening,
So the. And the formula is
That answer at this point
yeah, see.
is, this
So,
doesn't make sense.
Our
Should be
more
switched
mass
to, right?
is 18.02.
They're switched.
Yes, the mass always goes with the unit of mass.
Grams. 3.65.
I mean, I believe
We're gonna use the word mass, but that always goes with the unit of mass. This is the atomic mass unit, so it always is gonna go with this.
In moles on the top. So our
Used for particle.
1 gram.
And then, now which one's smaller, particle or mole? So this number always goes to the smaller one.
okay.
So once you stop intermediately, then you can pull the numbers out. This would give you an answer in particles. This would give you an answer in moles.
Oh, yeah.
So I have to clean that up a little bit, but I'm right track.
Okay, so should have some.
Oh, yeah. Yeah. Okay, yeah, so that would be the 18.02 grams. Bottom. And then 1 mole. Yeah, because you're doing. You're dividing by the.
So it'd be one mole
I think
over 1.66 below.
Yeah, I think that's why.
Okay.
Well, it's because, okay, so I don't know why. It's,
Yeah.
if I use this. Oh, is this what it was? The formula and the particles, you go
This,
I think I wrote that one.
that's right.
Okay.
This set of prices, you need to get. Well, that makes more sense.
Yeah, because we tried to do it both ways. We
I think you
did,
should have the same answer either way.
okay, because when we did,
Because here's probably
Oh, yeah.
first this.
Yeah.
This is a
Okay.
mass, which goes with the rest of the mass.
okay,
And that's why it's perfect.
because we were thinking of it. Okay.
So this is a mass. So that's what particles.
I knew that
The mass always goes with the mass. So formula mass.
What would be the difference?
Um,
And what
and
would be the mass?
whatever. Always go with use.
We just solved.
Okay,
I'll show you.
Use that
Yeah,
as
just and then each one after, I'm just, because then you're getting
I
particles
think
and
just
mass.
this one right here.
Differences.
Because that's what we got the first time. We're like, oh, something's not right.
So fix that so that your readers can see what's going on.
Okay.
Um,
I'll rewrite it on this
Okay,
other
and I'll
paper.
sign on the one, whichever one you read, right?
So, we have to go to. Yeah. Just to give you an example,
Because we're young.
Yes. Great. Yeah, I know how to do that. But we need to.
Okay, so from the beginning, what we need first is your multi-pass. And you have to go to the periodic table and find them. So, okay.
Yeah.
I need to show you.
So we're just adding.
Did you do it right?
So we're just adding.
I don't know if anybody else is still doing that. However, you missed one before these things. No, you were here for the whole meeting training. You were here. The day we were playing the card game. I couldn't find it.
I couldn't find it on what?
It's still there. I couldn't find it. Okay, ask me about that later on, and I will get resolved for you. Just go ahead and bring that in.
Because I've been having a lot of problems.
I know you have, so I want to make sure that we're on the same page.
That's why just kicking my butt too.
I can't look at the quiz and just.
She showed me how to do it.
I can't, no, I can go back and look. It's just really, I couldn't even get the access to it.
That's what I'm trying to figure out.
You shouldn't have to go through the Blackboard.
I tried Blackboard, even my Pearson, the site was just down,
Oh,
I
it's
guess.
Pearson, which is now.
Yeah, I just had a.
Yeah, Pearson's usually pretty good, but
Not so much.
Question, then that's, but for the Muller mask, is it grant or is it you grant?
it depends on where you're using it.
So we are.
So if you're using it here,
And this is the mouse and grams of
we
this.
typically call it formula mass. So if I'm going to try to use formula mass is used in one word. If I'm calling it molar mass, that will tell me how many grams.
That's what I thought.
So it's the same number though, either way. So that's why I didn't specify it. Usually when they say MM, they're not saying whether it's a molecular mass or a molar mass. They don't put units on it because
So
they
now,
use
because
that.
we're using grams.
So for the test, do we need to put the unit on it? Or just put the
What you
number?
will in your setup. For example, you put the units on it here.
And we
So
know
it's
that
understood.
because of our
What is that?
we're
We're
gonna
gonna
send because this is a package.
Did it right?
Our morning classes, they were just tired.
I like doing these when we do it during class because it makes more sense when you're actually doing it.
Absolutely, it does. And that's why I try to give you something as often as I can.
Yeah.
They really do help. So get everybody's name on it, get a picture of both, yeah, so you know the drill.
To get to.
Let's do one at a time. So just how to write it, just how to write it. Grams here.
Do I need to take
Notes, avocados,
It's
and
both. Get everybody's names on there.
So we only use it when we're converting with the other. So we know that we use avocados numbers in this. We also use avocados number on this. We use avocados number.
Yes.
So that's why you're gonna go ahead and it always goes with the
Real quick here.
so this will go. The smaller grams.
So which one goes with the smaller unit, the particles?
So no, that's this part. Now it's a completely different thing. Now we're gonna go from units to what's our next circle. Particles, right? So let's get rid of the units. How do you get rid of the units? Erase. So we just now we're getting rid of units.
What's which one's
ART. Just break
Oh, just
ART. Now you can change.
Yeah, it's still there.
So there are no 6.022
You
No.
can any kind of work, I
So
think highest score.
go to.
Good, get that out. Everybody
says
drops one.
Now, how the only
And
way,
it was already due,
what is the
doesn't
only
mean you
number
can't
you
take it
can use between Williams and
Yes, yes, because it's important that you guys get this.
Oh, between.
No, it's gonna give you different times, different questions every time.
Right.
And it's gonna tell you whether, what the correct answer was, so you can learn from those, and that's really what it was about.
Okay,
So,
we need to use this.
get it,
Right, and the.
and get in there, get
That's what I'm saying.
I got one.
That's
That's right, that's why I wanted to slow you down.
Yeah.
You're going way too fast. So,
I don't know if anybody else is doing this.
with your. And then your maps and your maps.
But that'll still go.
Yes, and it is gonna be your
That's you.
forms. It's not,
Because she always like
That's
has
good.
like one day where
I wouldn't make it that complicated. It doesn't mean, it's not, we're not measuring.
Either way, we know that
We
it's
just know.
whatever.
I'm lucky for you. You're trying to see.
So, and then it's gonna go to one. Now,
Yeah.
let's go ahead.
But like I said, everybody drops one and maybe just, you know,
Yeah, we're gonna write it out.
So now the last one, get rid of one.
I want to go back and do them. I appreciate your material, but I wasn't sure. Is it still accepted after the test for them?
it is, but there's a certain percentage on my day.
My date, so we don't use about how long after the fact
Yeah.
it's been due.
What happens at the end of the term, I drop one. So you can go back to this one. It may not help your score, but it would help you. What would help you most is when you go back to the quizzes, chapter quizzes. Yeah, do the homework if you want to for you, it may not count that much.
It'll, I mean, it'll count on more counting.
Exactly.
I know.
And
And I actually have
Dodgers. And also as
Is it here?
so there's ways to measure the same yourself.
Okay, so, and is it on? I just like it first.
You go here to settle selection. You can use the chapter quizzes. And so there's one for every chapter. If you do them before the test, then.
Okay, so now you want to go with
So
one.
if you do the before the test, there's credit. If you do the anytime before the test, whichever is your lowest exam score, will be replaced
So
by
for
that
a
average.
smaller part,
Oh, thank God.
that's where you can do.
And that's why I do that. But I know that for whatever life happens, so I have a backup for you.
On here, there's a small, so I can.
It's on the outside because I've always been in
It's not safe.
Oh, okay.
So between the small
I
side
will do that.
and the large side.
Because it's supposed to go to,
Well,
I thought it can go to small or to large.
no, it stays with the small.
like data.
So between particles and moles was that.
So the particles.
So that's where you're. Okay, now where you, that's right, so now you've done everything.
This is our.
So I did what I did. So for how I organize, I do like this. This is gonna give you, because that's how you solve. You solve this.
Got that.
Multiple choices, 'cause that's
Mhm.
your
Yeah, we
your
know.
intent.
Mhm.
Doesn't matter. Then it'll be the sum of this one.
Plus it plus it
divide by this. Will be and then
74.5.
And it's divided because it's
on the bottom.
that was here.
right, and then the sum of this divided by this will be moles. So
Oh, wow.
now we have this will be here,
Okay.
That's
and this will be
so everybody who hasn't yet reported in.
will be your four.
All right, group 5.
I like that. Yeah, the sum of
This is
this.
awesome. Because look, that I'm a student. I would know I need to get my views. Okay. Thank you.
Yeah.
Like 0.3.
No, just
Are you, okay, because this is, you see, this is 9.
No, that one. Do we have to, yeah.
This is backwards. Avogadro's number always goes with a small number. Molecules are tiny. Moles you can see. So it takes Avogadro's number always goes with a smaller number.
Times. Okay.
Yes, so it's gonna change that outcome. So again, the small, since molecules are small, remember this is, just small size, large. Avogadro's number always goes with right, so we get grams, and you have the reverse here. And this is a small size.
Okay.
So I can see you guys have been struggling with that.
Yeah, definitely.
So we're going
Wait, so
from grams
this
to
would be
cubes
we need to
of
do
the two. This is a small side, so Avogadro's the
I just
So get that cleaned up, because that's gonna change your outcomes.
we don't have to worry about it.
So if you got going on,
I mean, my thing is that.
okay. The setups.
I'm just saying,
Setup
while
this
you're learning this,
number
don't worry about that. Learn this and then worry about it.
This is,
Oh,
Yeah,
that's calcium.
yeah.
Yeah.
Switched it and it's got the right one.
Yeah, so yes, I'm okay with that. Now, molecules to moles isn't true.
And I could use this, or what do I do?
Yeah,
This
you can
is
do
always
use
small,
it here.
this side is
All
large.
you have to do is
Avogadro's number always
Okay.
goes with the small.
Beautiful.
see how that works. That's why I did it
Always,
this way.
always, always. So of the two,
Oh, yeah.
molecules is the smaller one.
There is, they are.
So you have the right number, but it's associated with the wrong thing. So molecules are little, moles are big. That gets us 2 moles. Okay, and that, we fixed it here.
Are you going?
Then, this is not the right number.
Keep going, James.
2, 2, I'm not sure what that number was, but
You said that's fine. Do some
then that gets us 2 moles. So whatever that number in moles is, for 1 mole is that molar mass. Let's see how you're not relating it to any number you're working with. Continue.
I guess we could. Whatever answer we get.
Okay, yes, these are the right numbers, right? That now gives you your starting point from here, and I can go from here to here. So whatever number you get here, is here, and this is your relationship.
That's what I was like saying. Yeah.
You didn't show me setups at all.
I don't think that way, but I think.
But you have to show me, no, you have to show me the setups. Unfortunately, that's half of the game.
It works.
So you need to show me what your relationships are. Dimensional analysis, part
I'm really
2.
dyslexic. So
Sorry, it is what it is.
There's no. That is.
There's the formula best for the
Formula
sources.
best and all of those are the same thing.
Same numbers,
Just
different
adding-
measurements.
Adding the two.
Yeah, and it's like, not all messy.
In that graph, it was.
Right.
It takes me a while to do things, but it always looks nice when I'm done. So I know,
Because you
so I
know how
can
to make
go,
it look
well,
nice,
because if I
that's
go
good.
back,
Yeah,
if I go back and I don't know what I'm reading,
exactly.
what I do.
I need something good. Something like that.
This is my phone.
From high school.
My good phone broke, and this is my phone from my storage from my
Right?
Like,
Like,
it's
so I'm
not-
trying to upload pictures, you know, and like, I just let you copy posts.
Oh my, are you,
This,
what
this
do you have?
website will be the main one system.
Oh,
I
no.
thought we came up with a better
You have
way.
an LG,
Okay, so with this one,
Fine,
what
say
we're gonna
because
do.
if it's an iPhone, you have to make sure that you don't, not.
Yeah.
I can make it.
Give me
for
the-
that anyways.
Just
So,
I just can't. No, this is, I have this.
shade.
So.
I
Three.
guess this way.
Search.
That's right, you just got a high
Oh,
school.
wait, no, this one you can't do that. You can, because you're using the website. You're gonna go to your
Look at
photo
this.
library.
I dropped one when I
There
worked
it
at the
is.
hospital, and I.
There it is.
Like I've already
Girl. And look at that.
That's what it was. Okay, yeah, because I remember.
So go to
we
their
figured
website, insert a
Well,
file,
File, not photo.
and then it works like a dream.
Yeah, because I was sitting over there like,
I just changed
Sure.
some
I turned my head out, turned my hair out.
It's just- Yeah, oh, yeah. Oh, yeah. Feel it. See, now you can't say it's a bane of your existence, because it works.
I need a big car. All kids need some of that. I need a big car. And I'm in a little bit. I need to trade that. That's my favorite car too. Yeah, I need to trade it. I need a big car.
Okay, give you a couple more minutes, but you need to reconvene in your usual spots. Take a break if you need to.
We did number one. Is that number seems really high for
It could be.
goals.
It does seem very high, but it might have been a big number. I made no effort to make these pretty numbers. I just wanted to see if it was that number. Your number.
That's number one, yeah.
Oh, here's the problem. This is a mass. Mass is how you look at a mass. Which of these is a mass? There you go. So that number's upside down, and then that number depends on that. Check your. Yeah. Particles are either.
So I can just turn some have another one with that.
That's a mess. That means it needs to be precious. That's the one. So,
I knew what I
they're
was
not
doing.
gonna finance anything.
Well, I told you.
Your book are really big.
Did you finance?
Buy it outright.
Oh.
And I financed the car that I just broke on me. And I.
Good times.
Just around. It's good, I'm breathing.
Yes. It is. All the
So I'm selling the car.
My daughter graduated high school from here. She was looking at what her choices were. I said, well, this is how it works. You're my stepdaughter. Until 2 years ago, you were not an obligation for me financially. And so I don't have savings for you. And her mom never saved anything for her. So I said, this is how much we can contribute. Here's the moles, here's the molecules, this is upside down. She's a little one.
Oh, I wrote it backwards. I did it right on the other one. I just, when I transferred it over.
And this number looks way off. Really? Because Bobby Dodger's number is 6.022, even the 23rd. This should be a number somewhere in the 20s. Same thing here. I think you may be using 13. So check your value. Maybe we said, anything you want to spend in excess of this is on you. And this is how much you'll be paying per month. Okay, you're using the wrong E. This is the E. This is natural long base E. And now we have discovered a product. All right, so that's an easy one to fix. So the way you enter it is the 23rd.
Yeah, you probably get everything.
You don't have everything, but that's good to know, though. That's also clean that up, and you're almost there.
I mean, you know, I've got 3 kids, and I'm gonna when they get older, I still want to do for them what I can. But you're in
I did the same. So we told our daughter, this is how much we can contribute. We can't afford to pay much more than this. If you go to these are your schools, if you stay in town and go to UNF for your bachelor's and live at home, you don't have to pay for living expenses. When you graduate, we'll give you a car. And we'll maintain your car while you're in school. So she's in grad school, she came out debt free, we paid for college. You came out debt free. It wouldn't have happened if she'd gone anywhere else. All right. Molds to grams, yes. Grams to use, yes. We on it? Alex, you gotta be working on processing it this way. Now here's a general, since you had grams, you know that what you're trying to get rid of has to go on the bottom.
Well, that's what I'm in.
Where you're headed is gonna go on the top of that. Always, always, always. So you're gonna have to work on building this because this is going to be something you use wherever you're headed. My best friend who's a pharmacist, which I taught her this, she did how much easier her life was.
It's still your
All right, so
yeah, you will be
take a mold, we're going to post this.
It's just what you want to do is do the religion.
Get both your names on that. All right, so go ahead and find your spots, and we're going to continue here. No credit for it.
Okie dokie. All right, now we've talked about percentages before. Percentages come into play again here in this chapter. We talk about percent composition. In general, a percentage is a part compared to the whole thing, which is a fraction. And we could make any fraction into a percentage by relating it to 100 as our denominator, just like we've seen before. When we talk about percent composition, it's usually talking about a particular element, or it could be an ion if you wanted. Could be, for example, in sodium carbonate, what's the percentage that carbonate contributes? So if we're going to calculate this, the whole in this part is the entire molar mass, or the formula mass, or whatever you want to call it. That when I figure out how much the entire molecule weighs, I want to contribute, or I want to look at what mass is contributed of that specific part. So usually percentages are by weight. We've seen that before. It's just that the specific element we care about goes on top. The whole substance goes on the bottom as the molar mass, and then we can calculate that. Now, what do all percentages have to add up to? 100, absolutely. So the last one, the last element, is always found by difference. So I'm going to tell you that when I solved for the percentage of sodium and I solved for the percentage of carbon, this one was 100 minus the percentage of sodium and minus the percentage of carbon. And we do that so that they will always add up to 100. For some reason, and I have no idea why, almost always these are expressed to 2 decimal places. So if I were looking at carbon dioxide, I know that I'm going to have to figure out at some point what the whole thing weighs. So I know I'm going to have to figure out the formula mass. So for carbon dioxide, I've got 1 carbon that contributes 12.0107. Where did I get this number, by the way? Periodic table. I've got 2 oxygens at 15.9994, also from the periodic table. Where did the 2 come from? Yeah, it comes from the formula. There were 2 oxygens there. So when I add those up, that 44.0098 we were working with on the last page came from that. If I wanted to know about the percentage only of the carbon contribution, then I say, okay, well, carbon contributed this much. 12.0107 compared to the total 44.0098 times 100% gives us the mass of carbon. Say it's like 27.4 something rather. So if I wanted to know about oxygen, I could do oxygen 2 ways. One of them would be to look at the contribution of oxygen, 2 times 15.9994 over the total. Or I could say 100 minus the percentage of carbon. Should give me my percentage of oxygen because that's all that's left. So about now I get the common question, so why do we care? Why would we bother doing this? And the answer is actually one of application. You have just bought a house, you have a well on the grounds, and you would like to use the well water either for drinking water or for water for your animals. And it has a funny smell. And so you want to test the well water to see what's in it so that you should know whether or not it's potable or not. The outcome of most analytical devices gives you answers in percentage composition. And so what they do is they boil the water off, they look at the residue, and then they analyze it. And it turns out that we can, based on these percentages, we can actually figure out what the substance is. And so that's why we talk about them, because that's the outcome of most equipment. Now, if you had this kind of information, how would I know what the percentage is of nitrogen, for example? So how would I set it up? 1417 grams of nitrogen over the total. I'm sorry, I just couldn't hear you. 1417 and 0.4045 because it's my total mass times 100. And if I wanted to know oxygen, how would I figure that out? Yeah, 100 minus the percentage of nitrogen, whatever that comes out to be. So again, traditionally, for whatever reason, these are expressed to 2 decimal places. And so you don't have to worry too much about sig figs. What'd you come out with for that one? Which then makes this 74.06. Are we okay? So that part you've actually seen before. It's just that now we're applying it to a compound and we give it a different names when it's talking about a compound. So percent composition is very specifically talking about the mass relationships in a compound. Now we know from our law of definite proportions or law of constant composition that the percentages have to be a fixed amount for a pure substance. So in this, CO2, there's always going to be 27.4% roughly of carbon. And if I have a sample that I think is CO2 and it is any number other than 27.4%, then it's not CO2. It's not a pure sample, or it's just a different substance. That doesn't mean there can't be other substances out there with the same percentages. It's just that that number is going to be fixed always for that compound. And that's what the law of definite or constant composition was about. So what we're going to do is we're going to use these percentages to identify what our unknown is. And we have two ways of writing a chemical formula. The first one we call the empirical formula, which means observed. So this is based on your observations. Now, because we're basing it entirely on observations, we don't know for a fact what the substance is. And so the way that we express it is as the lowest whole number ratio of atoms. So empirical is always the lowest whole number ratio. For example, if I had a compound that was N2O4, his lowest ratio would be this, because they're both divisible by 2. Are we okay so far? Now, if I want to determine the empirical formula, remember that these are mass relationships, and chemical formulas are not. They talk about individual atoms. Or, for simplicity's sake, they could be talking about moles of those atoms, just groupings of them. So if we have a percentage, this is grams. It was based on grams. And so we need to be able to take the information in grams and convert it into moles, because moles can be used to describe our formula. So if we're given percentage, you're going to write somewhere on the page, assume a 100-gram sample. We could have assumed any size sample, but we're lazy. If I have 100 grams and my percentage tells me how many for every 100 of something, then choosing a 100-gram sample means that we can take this number and it's now our mass, 35.00 grams if I have 100 grams. And this would be 5.05 grams in 100 grams. So that's why we choose a 100-gram sample, because then our percentages become masses. Now, again, how does that work? If I have 100 grams of my sample, my percentage says there's 35.00 grams of nitrogen for every 100 grams. By definition, that's what percent means, is divide by 100. And so that's why that number is converted. Now, again, a mass relationship isn't a chemical formula. We're going to have to get it into the form of moles. And we know that if we have grams and we want to go to moles, what information are we going to need to connect them? Molar mass. And so for nitrogen, for example, looking up on the periodic table, bless you. I take a second to look at my setup here. If I have 35.00 grams of nitrogen, and I'm trying to go between grams and moles, grams go on the bottom, moles go on top. Molar mass is a number that goes with which of these two? Grams. So notice the way I set up my chart is so that this number will be divided by that number. Set it up in the direction you're going to be doing the math. This divided by that gives us the third value. And no, on a test, I do not give you this box. So you need to know how to manage the information. I'm going to do that for all of them. Which means that I now know that there's 2.4988 moles of nitrogen, 5.01022 moles of hydrogen, and 3.7476 moles of oxygen. Now, you've never seen a chemical formula that said N2.4988, H 5.01, and 3.7476, because we know that these have to be small whole number ratios, right? So the next two steps are to find first the lowest ratio, and the last step is to make it into integers. So the first thing is to take our mass and convert it into moles, because we know that our formula has to be a ratio of moles. Now, what's the lowest integer? Five? What are integers? Numbers that don't have any decimal places, right? And if you're talking about positive quantities of things, what's the smallest integer you could have? If you have any, you have 1. You can't have 0 of something or it's not in the formula at all. Would you agree to that? So what we're going to do is we're going to divide by the smallest number of moles so that that number becomes 1. That would be the lowest integer I could get. So which of these is the smallest number? This one. Now I have to do it to all of them. Why? Because it has to stay proportional. If I did it to just one of them, then I wouldn't have a ratio anymore. I will have changed the ratio. Now at this point, leave 2 decimal places. Any more than that is unnecessary. Out of 2 decimal places, that leaves this number 1. Well, obviously, we don't need to have decimal places. 2.00505 and 1.50. The 2 decimal places, 2.01. Now, the reason I say 2 decimal places is that's really all you need to make your next decision. Again, this is a ratio, but nobody says that it's going to be a whole number ratio yet. So our last conversion or our last step is to make sure everything ends up being an integer. We're going to look for common fractions. 1/4, 1/2, 3/4, 1/3, 2/3. Now in decimal form, 0.25. What's this in decimal form? 0.5. What's 3/4? 0.75. 1/3. 0.33 and 0.67. Yes? So that's why I say look for 2 decimal places, because with 2 decimal places, we can recognize these common fractions. Do I have any of those common fractions? Yeah. This one is clearly a 1/2 multiple, yes? So because this number is 1 1/2, to deal with the fractions thing, we're going to multiply by the denominator of the fractions. And then round. Now, if I didn't have any fractions, then I would just round because I wouldn't have any. The denominator would be 1. So this fraction is 1/2. So his denominator is what? 2. I have to do the same thing to all of them or I'm not keeping it proportional. 2, 4, and 3. Which means that my empirical formula, N2H4O3. Because 1.5 times 2, 3. Yeah. Yeah, I'm going to tell you, you're not going to end up with that, but you would multiply by the least common denominator. But I've never seen a problem that's ever been like that. But that's how you would manage it. All right. So let's look at another one. These actually are kind of fun. You just need to go through the process. Again, we have 1, 2, 3 elements, carbon, hydrogen, oxygen. What's the first thing I have to do? Which is what? How do I get the mass? Because right now I have percentages. I have assume 100-gram sample so that I actually have gone from percentage into mass, which is then 76.57, 6.43, 17.00. And I know that I'm going to have to go from mass to moles in my first step. What information relates grams to moles? The molar mass. Molar mass for carbon, 12.0107, 1.00794, 15.9994. You might wonder, Nance, why are you using such long numbers? Why don't you just round to 12, etc.? And the answer is, I don't want to round too early or it makes my recognition of the fractions a lot harder. Then I'll miss a fraction that was actually there. So you really need to work with good numbers, at least 4 sig figs on your molar masses when you're doing this so that you won't have that issue. Number divided by the second number. All right. So I know I've got 6.375. Again, keep at least 4 sig figs there. 6.379 and 1.0625, I think. Those lines. What's my next step? Yeah, I need to find my lowest lowest ratio, which means I divide by what? The very smallest one. And again, I have to do the same thing to all of them. Divided by 1.0625, divided by 1.0625, divided by 1.0625. So 6.00, 6.00, and 1. Do I have any fractions this time? No. In fact, I'm really lucky. So if I multiply by denominator, my denominator would be 1. If you're just dying to do the same thing, there are no fractions. So your denominator is by default 1, but you would need to round. 6, 6, 1. C6, H6, 0.
Why do you say round if?
Well, these numbers happen to be nice. They're not always nice. Sometimes they're really ugly. And it depends on, realistically, it depends on how accurate your measuring device is. So if there were a precision error in your device or your device needed to be calibrated, these percentages theoretically are coming from some equipment. And so if you're working with experimental numbers, sometimes they're not pretty.
This is the formula for this disinfectant.
Yes, this is the empirical formula.
Like you know,
Since there was no fraction,
but like
then we would multiply by the denominator and then round. Always. Because we're going to have to round to at this point, we're making it an integer. So step 2 is to find the lowest ratio. Step 3 is to make sure everything's an integer. And so if it was a fraction, then we need to make sure that nothing's a fraction anymore. And then we round.
For the denominator,
Mhm.
I think she was asking, do you pick the smallest denominator and then that's what you multiply by?
Well, there were no fractions here. This is the question that Jeffrey was asking earlier. You said if I had multiple fractions out there, I've never seen a problem like that, but if you did, you would pick the least common denominator of all of the fractions that were there. And again, in this class, we're only looking for thirds and quarters and halves. So yeah, that's the same issue. Now, it turns out that the molecular formula, this is a really important idea, the actual molecular formula is a whole number multiple of the empirical formula. And the multiplier that we need is going to be based on the mass. Now think about it for just a second. What I'm telling you is that earlier we looked at the N2O4 and we said his empirical formula was NO2. If this is the actual formula, what we call a molecular formula, and yes, in this class, that will always mean molecular formula, MF, you'll notice that the actual molecule is bigger by some integer. If it's twice as large as it appears to be, then it should weigh twice as much. Would you agree to that? Well, here's the thing. The actual compound mass is measurable. We use a mass spectrometer, and there's a way to measure the molecular mass of any unknown substance. So this one we would be given. Then I can compare it to the mass that my empirical formula gives me. For example, for glucose, the molecular mass of glucose is this, and its empirical formula is CH2O. So my question is, what's the actual molecule? Well, if the actual molecule weighs 180, and my empirical formula should weigh roughly 12 from the carbon, 2 from the hydrogen, and another 16 roughly from the oxygen, should weigh about 30. That means the actual molecule is 6 times the empirical formula. Would you agree to that? Because it weighs 6 times more. So if the empirical formula is this, the molecular formula is going to be C6. 2 times 6 is 12. 0.06. So let's look at the next one here. Here's a molar mass. This is the actual mass. And we're told a percent composition. Okay. Carbon, hydrogen, and oxygen. What's our assumption? Assume 100-gram sample. That means 40.0, 6.72, and 53.3. What's my first step? What do I need to do? I need to find moles. To find moles, what am I going to need to know? Molar mass. 12.0107, 1.00792794, 15.9994. When I did that, I came out with 3.33, 6.67, and 3.33. What's my next step? Sure, I want to find the lowest ratio. So I'm going to divide them all by the smallest number, which could be this one, yes? Two decimal places, 1, 2, and 1. Do I have any fractions? Nope. So if I multiply by a denominator and then round, 1, 2, and 1, my empirical formula is CH2O. Which, interestingly enough, is the same one from the previous example. So what's the formula mass of our empirical formula? It's going to be about 30 because it's the same formula. Right? That's 1 carbon and 2 hydrogens and 1 oxygen adds up to about 30. So our multiplier is going to be our actual mass, 180, over our formula mass of 30. And in this case is also 6. Which means that the molecular formula for this substance is what? It's not really a surprise because simple sugars, allose, glucose, fructose, they all have the same empirical formula. More than one thing can have the same empirical formula. More than one thing can have the same molecular formula. Yeah.
How are we getting?
Okay. Are you okay with how we got the empirical formula?
Yes, I've seen
Okay.
that.
So now I need to calculate what his formula mass is. I've got 1 carbon, and they weigh roughly 12. I've got 2 hydrogens, and they contribute roughly 1. And I've got 1 oxygen that contributes roughly 16. And for this one, honestly.
Is this on the periodic table?
Yeah.
This weight? Okay.
Yeah. I'm using very rounded numbers because for this one, it's always going to be a rough number anyway.
Okay.
So, yeah, carbon 12.01, hydrogen 1, roughly 16. So I'm using rounded numbers here because this is always going to be a real rough number. Yes. All right, and that's where we're going to end this for the evening, and I'll see you in lab in about 10 minutes. Thank you for asking.